So in this video, we're just going to continue with the radial equation. So continuing with our radial solution, we had guessed at the solution, at least for the S state, that's where the L equals 0 state, and we guessed, and we got a solution here for big R, for this lowest S state, and we got the energy, and this energy happened to be the same one that Bohr got for his lowest energy, the minus 13.6 eV, and A naught was the Bohr radius. Now, if we just wanted to know what the probability was as a function of R, so the probability as a function of R, remember, most of the time our probability was psi star psi, but we have to include the R squared in there. So it's really R star R, but you got to put the R squared in there because of this R squared right there. Because when I sum it up over from 0 to infinity, it better give me 1. So I need an R squared in there. So that's the probability as a function of R. Remember, the reason why it goes as an R squared is because as you go out, you're covering, your area is getting so much bigger that you have to compensate for that. That's why it goes as an R squared. It matters more when it's out there because it covers a lot of area. When you're in rectangular coordinates, you don't have to put anything there because as you may go out further, X, Y, and Z, it doesn't grow like that. It just, at all. So what do? If we just plug in R, if we square this and multiply it by little r squared, then this squared is 4 over A naught cubed, and then we have the R squared, and then the E times the other E is e to the minus 2R over A naught. So there's what the probability would look like as a function of R. Remember, this is a nice integral. It sort of saves a lot of time. Okay. Now, if I were to plot this out, what does this function look like? Well, if we plot out the probability as a function of R versus R. Well, the 4 over A naught doesn't, that just scales it. If I looked at each one of these, if I just looked at R squared, we know what that looks like. Maybe I'll put that in a different color. We got R squared looks something like this. There's R squared. And e to the minus something, e to the minus x or something, just kind of goes like this. Right here. And so what are we doing? We're taking the product of these two. So if we take the product of those two, you notice right here, 0 times anything is going to be 0. It's going to be really low. Likewise, when you're out here, this 0 times a big number is still close to 0. But you notice right here, this times this is going to be even bigger. And so it's going to look something like that right there. So this is what the probability is going to look like as a function of R. You'll never find it in the nucleus, right here, the probability is very low, and you'll never find it way out there. So it looks like it's got a, wonder where you're most likely to find it right there. That's where you're most likely to find it. If we wanted to find out where you are most likely to find it, I guess I could just take the derivative of the red curve and set it equal to 0. So really all I have to do is take the derivative of this and set it equal to 0. Now, this doesn't matter right here. All I want to do is maximize this. Because if this is maximum, the whole thing is maximum. So I'll just take the derivative of what's in the circle. Okay, so that looks like the product rule. So we got the first, R squared, times the derivative of the second, which is e to the minus 2R over A naught times minus 2 over A naught, plus the second, plus e to the minus 2R over A naught, times the derivative of the first, which is 2R. And we'll set that equal to 0. Okay, and then we'll just, first of all, we can cancel some stuff. We can divide out the e to the minus that. We can factor that out. That can never be 0. We can pull out an r, and r equals 0 would solve this. The slope goes to 0, but I don't want to find where that point is. That's a minimum. That's not a maximum. So I'll get rid of the r solution. And so we're left with just minus 2r over a naught plus 2 equals 0. Throw this on the other side. The 2's drop out. This is a 1. So it looks like r is equal to a naught, the Bohr radius. That's where I would expect to find it in the lowest, which is kind of what we expected. This is a naught. So this is the most, that's where you're most likely to find it. The probability is the highest. What's the probability that r is less than this? Probability that r is less than a naught. You're within the Bohr radius. Well, wouldn't that just correspond to this area right here? It would just correspond to that area. Well, if we wanted to solve for that area, I guess we could just integrate this from 0 to a naught. So this thing would be, if we just integrate this, I'll pull out the 4 over a naught cubed. And then we just want to integrate this from, but we only want to integrate from 0 to a naught of r squared e to the minus 2r over a naught dr. That would give me the probability. Now, I can't use this integral to solve that because this is only from 0 to infinity, and this is from 0 to a naught. So I can't use this. So it looks like over here I'd have to use parts twice, probably. If we do parts, then I could let u equal to r squared, and dv equal to e to the minus 2r over a naught dr. Okay, and so du would be 2r dr, and v would equal e to the minus 2r over a naught times minus a naught over 2. Okay, so this integral right here would be, I'll pull out the 4 over a naught cubed. And so we've got the integral of here. We got uv, which means we've got this times this, which is minus a naught over 2 r squared e to the minus 2r over a naught, evaluated from 0 to a naught, minus the integral of v du, minus the integral from 0 to a naught of v. Well, I have a minus there, so that's going to turn that into a plus a naught over 2. We've got the e to the minus 2r over a naught times 2r dr. Okay. So, what does that give me? That gives me 4 over a naught cubed. Now, when we plug in 0, it gives me 0. So all I have to do is plug in the a naught up here. So we're left with minus a naught over 2. And then that gives me an a naught squared. So it's just going to make this cubed. And then we have a e to the minus, a naught and a naughts cancel, it's e to the minus 2. So that's this term when I plug in both, plus a naught over 2. Now I have to, the 2's drop out, so we'll cancel those two 2's. So we got plus a naught. Now over here, I'm going to have to do parts again, right here. So we're going to let u equal to just r, and dv will equal e to the minus 2r over a naught dr. Same thing we had before. E to the minus 2r over a naught dr. And du is equal to dr, and v will be exactly what it was before, e to the minus 2r over a naught minus a naught over 2. Okay, so this thing's going to give me uv, so it gives me this times this, so it gives me, I'll pull out that first, minus a naught over 2, e to the minus 2r, sorry, that's not, yeah, you're right. It's uv, which is, there's e to the minus 2r over a naught times r, evaluated from 0 to a naught, minus the integral of v du, 0 to a naught of v, which is this, well, e to the minus 2r over a naught. I can pull out the minus, that's going to make this a plus, a naught over 2 dr. Okay. Which equals 4 over a naught cubed minus a naught cubed e to the minus 2 all over 2. And then this will give me, plugging in 0 gives me a 0, so I just have to plug in the a naught. I get an a naught, a naught, a naught, minus, so it's minus a naught cubed all over 2, e to the a naughts drop out, e to the minus 2. Is that exactly the same term? Okay. And then we have this term right here, which is plus a naught squared over 2. And then we just have to integrate this. Well, the integral of that is e to the minus 2r over a naught times a naught over 2, evaluated from 0 to a naught. Okay. Which is equal to 4 over a naught cubed. Now these two terms, looks like I can combine them, it's just minus a naught cubed e to the minus 2. And then this term over here is plus, now when we plug in a naught into here, we get an a naught cubed over 4 e to the minus 2, okay, and then subtracting off, plugging in 0. If you plug in 0, this just goes to 1. So it's just a naught cubed over 4 minus a naught cubed all over 4. Okay, this is the probability. Now, if the a naught cubes all drop out, it should be unitless. It's a probability right there. If we multiply by 4, then this is minus 4e to the minus 2. The 4's drop out, plus e to the minus 2, plus e to the minus 2. Actually, wasn't this one right here, I think was negative because, oh, okay, yeah, that one's right. Then this one over here, I just wanted to make sure, when we integrated this, this was minus a naught over 2. Sorry, there was a minus there. So if that one is a minus, which means that these two terms, this was a minus right here, this which made this one, let me just remember here. Here we had a naught, we already plugged that in, that took down to here, and then this was that with a minus, and then when we plugged in this right here, 0 to a naught, when we plugged in a naught, this thing became e to the minus 2, but this was a minus. This was a minus right there. And then we subtracted off, plugging in 0. When we plugged in 0, that means this one was a plus. Okay, just wanted to get those two minuses in there. So when we multiplied by 4, this was minus 4e to the minus 2. Then this next term, the 4's drop out, and we just get minus e to the minus 2. And then the last term is plus 1. Okay, which is minus 5 e to the minus 2 plus 1 right here. Well, minus 5 e to the minus 2. If you plug in this number right here, this right here is like 1 over 8 or something like that. 5/8 minus 5/8 plus 1. 1 minus 5/8 is like 3/8. It's about 0.32 or something like that right here. So the probability that you're within this would correspond to 32% of the area. And the rest, that would mean that this area out here would be like 68% of the area. Now, if I wanted to get the expectation value for R should be at the centroid of this. Well, we already know that this peak is a little over on this side because there's only 32% of the area on this side. So I would expect the expectation value should be out here, somewhere where you have 50% of the area on either side. If we wanted to get the expectation value, R, remember, it's just R star, and then whatever the operator for that is, that's just R, and then we need to put the R squared dr, a lot of R's. Again, this R squared is due to the volume. That's because I want to find the expectation of my operator, and we just sandwich it in, and this goes from back to 0 to infinity. Now we can use that old trick right here. We don't have to do parts right here. So this is equal to the integral. Now if we square R, it still gives me the 4 over this. It's just going to be this with an extra R in it, because this was just R squared. Now we have an extra, it'd be R cubed e to the minus 4 over a naught cubed, and then it'd be R cubed e to the minus 2R over a naught dr from 0 to infinity. Again, I want my integral to look like this so I can take it really easy. So we let all of this be x, this 2R over a naught. So x is equal to 2r over a naught, or r is equal to x a naught over 2, or dr equals a naught over 2 dx. So plugging these in, we get 4 over a naught cubed, 0 to infinity, r cubed, this cubed, I'll pull out the a naught cubed over 2 cubed, I guess I'll just call it 8. And we still got the x cubed. And then we have the e to the minus x. And then we have the dr, which gives me another a naught over 2 dx. And we know what that integral is. Just comparing it to this, it's if n is just 3. So this is just 3 factorial. 3 factorial, this is just 3 factorial, which is just 6. So now we have the a naught to the 4th over a naught cubed is just a naught. And then we have 4 times 6 all over 8 times 2. 8 times 2. Well, this is just 1/2, and that's 3, so this is just 3/2 a naught. 3/2 a naught. And we did say it was bigger than a naught, so that would be 3/2 a naught. Okay, so there's my expectation. That is 3/2 a naught. Well, what about if I want to get the uncertainty in r, I'm going to need to get r squared. So let's just figure out what r squared is. Well, it's going to look a lot like this, except it has an r squared there. So that's just going to make this r to the 4th. Okay, so this is just going to be 4 over a naught cubed r to the 4th, e to the minus 2r over a naught dr, 0 to infinity. We'll use the same substitution here. So this becomes 4 over a naught cubed r to the 4th. That would give me, pull out the a naught to the 4th, well, a naught over 2 to the 4th. And then in the integral, we still got x to the 4th. We still have e to the minus x. And then the dx, or dr, will pour out another a naught over 2. A naught over 2 dx from 0 to infinity. That will just be 4 factorial. So this is just 4 factorial, which is 3 times 2 times 4 times 3 times 2, which is 24. So this is just 24. So what do we got? We got the a naught to the 4th, a naught to the 5th over a naught cubed is a naught squared. And then we get, this is 2 to the 4th, which is 16. And so we get 4 over 16, that's 1/4, 1/8 times 24, which is 3. 3 a naught squared. So that's what the expectation value of r squared is. If I wanted to find the uncertainty in r, what do? We take the square root of r squared minus r squared, which is 3 a naught squared, the square root of 3 a naught squared, minus the expectation of r was minus this squared, which is 9/4. A naught squared. Pull out the a naught, and we're left with 12 fourths minus 9 fourths, which is 3 fourths, which is square root of 3 over 2 A naught, which is what, 0.866, we're used to that number, A naught. So you'd have to go out from here 86% to get plus or minus 1 standard deviation, 0.866 E naught. Well, what about the momentum, the average momentum? Well, this is a bound state right here. You're bound, anytime you're bound, you have just as much likely to be going one way as you're going the other way right here. So your average momentum is always 0, especially for a bound state. You probably should have remembered that for the quiz you took last week, because I asked what was the average for a bound state. This is always 0. Okay. Now, what about the P squared? That's not going to be 0. How do we do that one right there? That one we have to be a little tricky right there. Because before we said the P squared, at least in one dimension, was minus H bar squared, the second derivative with respect to X. But we're in 3 dimensions here, and so we don't want to use some big mess right here. There might be an easier way to do it, and there is. We could just say, well, we could say P squared over 2m, that's the average kinetic, minus E squared all over 4 pi epsilon naught times the average 1 over r. That's the potential. That should just be the energy. There's the energy. We do know what the energy is for this state. We know 2 and m, and we could probably find this out, so we could probably get that just from this equation right here. That is, I won't plug in E yet. We'll plug in, remember, E is right here. There is E. Okay, so what I'll do is I'll move this term over, and then we'll multiply it by 2m. So P squared is equal to, if I add that over to the other side, first of all, it's 2m E squared all over 4 pi epsilon naught, average of 1 over r. So that takes care of that. And then we also have plus 2me. Okay, I think I got that right. We move this over, multiplied it by 2m. Now, I know what E is. I just need to get what this is, this average of 1 over r. Well, instead of putting an r in there, if I want to find the average of 1 over r, I just put in a 1 over r. If I just have a 1 over r here times r squared, that's just going to be r to the 1 power here. So it's just going to be this with just r to the 1 power. So this is 4 over a naught cubed. We just have r to the 1 power, e to the minus 2r over a naught dr, from 0 to a naught. Sorry, 0 to infinity. Okay, now again we can use this same stuff, turn it into x's. We replace r, we bring out an a naught over 2, so we got 4 over a naught cubed. Then r gives me a naught over 2. We have the integral, we have an x. Then we have an e to the minus x. Then we have a dr, which is a naught over 2, another a naught over 2, dx. Well, this is just x to the 1 power. This is just 1 factorial. 1 factorial, which is just 1. So all of this is just 1. The 4 cancels with the 4. The a squared and the a cubed just gives me 1 over a naught. Okay, so that's what this term is right there. It's just 1 over A naught. Okay, well, so we get P squared is equal to 2ME squared all over 4 pi epsilon naught A naught. Well, let me see, what was our A naught? I just wanted to remind us, I don't think I have it written up here, but A naught is, here it is. A naught is equal to, so this right here, 1 over A naught was M E squared all over 4 pi epsilon naught H bar squared. That's 1 over A naught. Okay. So what do we have up there? We have a 1 over A naught because this was 1 over A naught. So I would put that up into here. We got an ME squared all over 4 pi epsilon naught H bar squared. Okay, that takes care of this term, plus 2M times my E. And remember, my E was right over here, which is minus ME to the 4th all over 2 times 4 pi epsilon naught squared, 2 times 4 pi epsilon naught squared H bar squared. Okay, well, let me see. Let me factor out whatever I can. Well, these two 2's drop out. This one drops with that one. We have an M squared in both terms, so I'll factor the M squared out. We have an E to the 4th. We have an E to the 4th. I'll factor that out. We have a 4 pi epsilon naught squared and 4 pi epsilon naught squared. We'll factor that out. We have an H bar squared. We'll factor that out. What's left? 2 minus 1, which is 1. Okay, so there is the P naught squared. You notice I could put that in terms of, maybe I'll put that in terms of A naught, because E squared, if I were to square this right here, 1 over A naught squared is equal to M squared E to the 4th all over 4 pi epsilon naught squared H bar to the 4th. I almost have that up there. If I just had an H bar to the 4th, I would have it. So what I think I'll do is I'll put an H bar squared and make that to the 4th power. So now all of this is A naught squared in the denominator. So this is all H bar squared all over A naught squared. Okay, we'll leave it like that. Now, I ask, what's the uncertainty in the momentum? Well, it's the square root of P squared minus P squared. But that was 0. We already said that was 0. And so we just have to take the square root of this, which is just H bar over A naught. And now we can plug it into Heisenberg's uncertainty principle, delta P delta R. Delta R delta R was A naught times the square root of 3 over 2. There it was right there. So that's delta R. We had the square root of 3 over 2 A naught times delta P, which is H bar over A naught. A naughts drop out. Square root of 3 over 2 H bar, which is 0.86 H bar, which is definitely greater than half an H bar. Remember, that was the minimum. So this was all for the lowest state. As you go up to higher and higher states, it's just going to get bigger. It's not going to get smaller. So it doesn't violate the uncertainty principle. And so on the next video, we'll go through what are the other states. This was just the lowest S state right here. Okay.